increase the temperature of the copper enough that we've hopefully reduced the resistance. Let's see if we can see a difference.
Whoa,
Yeah.
that is cool.
Now the problem here is every time I try to move this, it creates an opposing magnetic field, so I have trouble getting it off, which is the tricky part. Let's try to drop it from the higher height. Now that's cool. So I reduce the resistance. The amount of heat that's being generated is less, not because it's colder, but because the resistance is less. So this thing is falling slower. It's falling slower because there's less resistance and there's less loss as these currents are circulating around. But we're not quite there yet. We don't have, it's not floating. It's getting close, but it's not floating. And unless we get something colder than liquid nitrogen, which we can do, but it's expensive, we're not going to get this thing floating. So if I were to continue lowering this down to absolute zero, what you may expect is that the temperature goes down, goes down, goes down, goes down, and it hits a steady value. It gets as low as the temperature you can get to, and it stays there. That's not actually what happens. What happens is if we were to reduce this below liquid nitrogen temperatures, down closer to liquid helium temperatures, which is the other cryogenic gas that gets used a lot in research, gets you down to about 4 Kelvin, which is 4 degrees above absolute zero. If we can get the copper down about there, what you'd see is that get to a certain temperature, and then it wouldn't continue on, it would just go to zero. So we start finite resistance, temperature keeps decreasing. You hit a certain point, zero. And that's weird, actually. What it says is that electrons that were flying through the material and bouncing off different atoms and different impurities in the walls have suddenly gone from bouncing less and less because it's getting colder and colder to doing nothing. They were having trouble getting through the lattice of atoms. Now they just move through it as if it wasn't there. And to explain what's going on is actually tricky. It's called superconductivity. And actually, superconductivity in metals like copper and lead is the big one they use. I just put way too much in there. Lead is sort of the typical superconductor. They transition to about 6 Kelvin, much, much lower than this stuff. But what's happening is, I can go into more detail if you'd like, but it's rooted heavily in quantum mechanics. What's happening? We basically, the electrons normally, they like to oppose each other. You get these things cold enough through an effect, it's actually got to do with the copper or iron atoms that are in the, you basically have positive atoms, negative electrons around them. The negative electrons move around very quickly and they can move through the entire conductor. But they don't like being in the same spot. You can't put them close to each other because first they have like charges, so they repel each other. The other thing, though, this is a little trickier, is if you can get rid of that charge, pushing them apart, they're like billiard balls. They bounce off each other, even then, through nuclear forces and stuff like that. You can't put 2 electrons on top of each other and have them occupy the same space, which makes sense. You think about billiard balls, you can't put 1 billiard ball here, put one on top, and expect one to fall into the other one. It doesn't happen. Well, it doesn't happen for things that are called fermions, like electrons. Most atoms and proton and neutron in the nucleus is called a fermion. It's got a spin 1/2. You're really interested. They're particles that can't exist in the same place as other fermions. You can't put 2 electrons in the same spot. One, because they have this Coulomb repulsion due to their charge. But even then, even if they didn't have it, you can't put them on top of each other. Bosons, on the other hand, so bosons are even a little weirder. Light is made up of bosons. Photons make lighter bosons. You have 2 bosonic billiard balls, you put them on top of each other. It'd be a really boring game, actually, of pool, but you put them on top of each other, they fall through each other. They don't interact with each other. Even if you can't bounce them off each other, they don't interact with anything else. They're characterized by a spin of 1. Spin is this quantum mechanical property that actually has nothing to do with rotation. They just couldn't think of a better name. Anyway, what happens here is you get a net attraction between these 2 electrons when you cool it down, and it's due to the basically positive copper atoms getting close to each other. So when an electron goes by, positive copper atoms are attracted to where that electron is. The electron moves off. Suddenly these positive electrons are still there. They move a lot slower. So there's a net positive charge here. It attracts an electron over here, it attracts an electron over here, that's a positive charge. What happens is they stick together and they become bosons. They can travel through, they basically pass through walls. So it's these walls that are creating the resistance. It's the bouncing off of the atoms and these interactions between these things bouncing off each other that creates resistance. You create a boson, it can pass through all those without interacting with anything, you can get superconductors. You can go even further than get things that are called supersolids that have no viscosity. So if I had a supersolid in this container, it would flow up over the sides and down across the floor. Or sorry, supersolid, super liquid. Super liquids don't have any viscosity, so there's no surface tension. They just flow up over the edge of the container and in. It was a real problem when they first discovered them, actually. They had to seal the top of the containers. There's even weird things called super solids, which I won't get into because I don't understand. But again, it's all this quantum statistics that's causing it. It's actually, when you think about it a long time, it makes sense. But if you haven't thought about it a long time, it's a tricky thing to figure out. Anyway. Regular superconductors we understand. We know why these things pair together. We know why the electrons pair together to form, they're called Cooper pairs actually. Again, named after physicists who discovered them, or explained them anyway. They bind together in these Cooper pairs and they can travel their resistance. We know why that happens with copper, and basically it's only going to happen with regular metals at really, really low temperatures, like well below liquid helium temperatures and lower. But one of the big things that happened in the last couple of decades, actually, 21 years ago, actually, is they developed these things called high-temperature superconductors. These aren't simple materials. They're actually mixtures of different types of materials. In this case, this is a yttrium barium copper oxide compound. And for the last 20 years, people have been investigating this because there are huge technological applications. The fact that we can use liquid nitrogen to make these things superconductors is the biggest advantage. The problem is no one understands how they work. We don't have any idea at all. We know there's probably Cooper pairs forming. We don't know why. It's not the same thing happening with regular superconductors. So these are a huge mystery, and it's one of the big top 10 questions in science is actually how do these work? What people have been striving for, who are less theoretically inclined and more practically inclined, is they're trying to figure out how can I get these things to be superconductors at room temperature? Because when that happens, that will totally revolutionize. Well, I'll give you examples later about how we'll do it. But the first thing is, if I were to, what I want to stress is that if I get this cold, I have a superconductor that has zero resistance.